When my sister was diagnosed with polycystic ovary syndrome in 2021, most conversations with providers focused on the reproductive side, including irregular menstrual cycles, hyperandrogenism, and ovarian cysts, while her weight gain, fatigue, and other metabolic struggles were largely overlooked. That gap reflects how PCOS has been historically viewed. PCOS affects 1 in 5 women of reproductive age worldwide, making it one of the most common causes of infertility. Yet, the official diagnostic criteria is centered on reproductive features and doesn't reflect the metabolic complications that many women with PCOS face. This criteria leaves out the metabolic complications that many women face, like insulin resistance, obesity, and type 2 diabetes. And these are just as important, as research has shown that metabolic issues account for nearly half of the total healthcare burden of PCOS. So recognizing and treating them early on is critical, which is where my research focus begins. Under the mentorship of Gabriela de Robles at the Nicholas Lab, we are studying the effects of prolactin, which is a hormone mostly associated with lactation, but its importance goes beyond the reproductive system, as it is present in almost every tissue in the body and acts on every major metabolic organ, such as the pancreas, liver, adipose tissue, and the hypothalamus, where prolactin plays a key role in maintaining metabolic homeostasis. Research shows that higher levels of prolactin have correlated with fewer metabolic complications. And knowing this, I will be researching the question, how does sustained prolactin exposure alter gene expression in key metabolic tissues in a PCOS mouse model? To examine our research question, we'll be using two groups of mice, both with a letrozole pellet implant, but one will be combined with a high-fat diet. The letrozole reciprocates the reproductive side of PCOS symptoms in mice, while a high-fat diet models the metabolic complications PCOS to provide a stronger model of PCOS. Then we'll implant an aslet pump that will continuously release prolactin into the mice. Finally, we'll take tissue samples of the pituitary, ovaries, adipose tissue, pancreas, and liver to check for changes in their genes using qRT-PCR and bulk RNA sequencing. By manipulating prolactin levels, we aim to learn whether sustained prolactin exposure can rescue metabolic and reproductive defects in a PCOS mouse model. This research will uncover mechanisms of prolactin signaling across tissues and may open the door to new ways of treating PCOS, not just as a reproductive disorder, but as a condition that also demands attention to metabolic health.